Imagine drifting beyond the final breath of sunlight, past the last gravitational whispers of Neptune, where the warmth of our star fades into an eternal frost, and suddenly the question arises, not just where are we going, but what even is this place we are entering? This vast cold ocean that stretches endlessly beyond the solar system's edge, an ocean not of water, but of darkness, distance, and the unknown. And in that silence, we begin to wonder whether the universe is more alive out there than we ever dared believe. For outside the solar system lies not emptiness, but a great frontier where science and imagination intertwine, where ancient cosmic particles drift from supernovae that exploded before Earth was born, where rogue planets abandoned, wandering giants float between stars without light or warmth, yet possibly hiding oceans beneath icy crusts, where alien solar systems host exotic worlds, orbiting twin suns, or dancing in gravitational harmonies. We've only just begun to understand, where the interstellar medium, though thinner than any vacuum on Earth, hums with energy, magnetic fields, and the whisper of ancient stardust, and where, beyond even that, the Milky Way itself stretches across hundreds of thousands of light years, a colossal spiral of stars, black holes, gas clouds, and time-bending mysteries that cradle our fragile existence in one unremarkable corner of one minor spiral arm, raising the question, if we are so small, why does it feel so significant that we can even ask these questions, let alone answer them? Because as we chart the outer edges of the heliosphere, where the solar wind slows and reverses under pressure from interstellar forces, we realize we've already crossed a profound boundary not just into interstellar space, but into a new age of understanding, where spacecraft like Voyager 1 and 2, launched decades ago, now transmit signals across unfathomable distances, carrying golden records of humanity into the void in the hope that something or someone might one day hear them. While telescopes like James Webb gaze deeper than ever into time itself, capturing faint light from galaxies that existed mere hundreds of millions of years after the Big Bang, revealing structures and phenomena that challenge our very theories of cosmic evolution, including the discovery of early supermassive black holes that should not, by current understanding, even have had time to form, suggesting that our models are incomplete, or that the fabric of reality might hold secrets stranger than fiction. And as scientists grapple with these anomalies, they also ponder the possibility of life, whether microbial or intelligent, thriving on distant exoplanets, orbiting red dwarfs, tidally locked and bathed in perpetual twilight, or orbiting sun-like stars in Goldilocks zones where liquid water could exist. And with every discovery of another Earth-like planet or atmospheric biosignature, the odds that we are alone shrink just a little. Though paradoxically, the Fermi paradox grows louder, whispering why, if life is so probable, we have yet to hear a single voice in the dark. And yet perhaps the answer lies not in the stars, but in ourselves. In our limited perception and tools, in the brief flash of time we've spent looking outward compared to the eons the universe has been unfolding. For outside the solar system lies not only new physics and new possibilities, but also new perspectives in time, space, origin, and destiny, forcing us to ask whether we are the beginning of awareness in the cosmos or simply a flicker in a vast continuum of life that has risen and fallen across a billion worlds. And all the while, gravitational waves ripple through the interstellar dark, echoes of cosmic collisions, black holes merging, neutron stars spinning apart, revealing the violent ballet of the universe in a language Einstein predicted a century ago, but which we've only recently learned to hear. And with every detection, we move closer to mapping not just the visible universe, but the invisible forces that shape it. While theories like dark matter and dark energy suggest that 95% of what exists lies outside our senses, outside our instruments, outside even our most audacious dreams. A reminder that what lies beyond the solar system is not merely stars and voids, but the key to everything we have yet to understand about gravity, energy, matter, time, and perhaps even consciousness itself. And as we stare out into this cosmic wilderness, we begin to grasp that space is not cold and dead, but a living, evolving system full of explosions and births, flows and fields, structures and stories waiting to be told. And the question of what lies outside the solar system transforms from a scientific curiosity into a human necessity, a quest that drives us to launch probes, build observatories, simulate galaxies, develop quantum technologies, and stretch the boundaries of imagination. Because somewhere out there, perhaps orbiting a dim, quiet star, a creature not unlike us might also be looking up and wondering if it's alone, if anyone else has made it past the barrier of silence, if some distant intelligence once looked outward from its own solar system and dreamed of contact. And maybe, just maybe, your stories will one day intersect across the emptiness between stars, and two lights in the dark will recognize one another and know they were never truly alone, because in the end, to explore what lies outside the solar system is to seek not only the nature of the universe, but the very meaning of our place within it. For most of human history, the universe was a mystery painted on the ceiling of the night sky, a canvas of light punctuated by unknowable stars. Early civilizations viewed the cosmos through the lens of mythology and religion, often assigning divine meanings to celestial patterns. The Babylonians tracked planetary motions with remarkable precision, the Egyptians aligned monuments with star risings, and the Greeks proposed early models of a geocentric universe, with philosophers like Aristotle and Ptolemy constructing systems where Earth sat unmoved at the center of all things. For over 1,000 years, this Earth-centered cosmology dominated thought across Europe, the Middle East, and parts of Asia, blending scientific observation with religious dogma. The turning point began during the Renaissance, when the Copernican revolution shattered the illusion of a geocentric cosmos. In 1543, Nicholas Copernicus proposed that the Earth orbited the Sunday, a radical idea that not only redefined astronomy, but questioned humanity's place in the universe. This heliocentric model was expanded upon by Johannes Kepler, who introduced elliptical orbits and mathematical laws describing planetary motion, and Galileo Galilei, who used a telescope to observe Jupiter's moons, the phases of Venus, and the craters of the Moon, clear evidence that Earth was not unique or central. These discoveries, though met with resistance from the Church, laid the foundation for modern astronomy and encouraged a scientific method based on observation and empirical evidence rather than authority or tradition. The next major leap came with Isaac Newton, who in the late 17th century formulated the laws of motion and universal gravitation. Newton's work provided the first comprehensive mathematical framework capable of explaining both terrestrial and celestial mechanics under the same principles. It suggested that the universe operated like a vast machine, governed by predictable laws. This mechanistic view dominated for centuries, guiding everything from planetary navigation to engineering. During the 18th and 19th centuries, astronomers like William Herschel expanded our understanding of the cosmos by cataloging thousands of stars and nebulae, even proposing the concept of island universes, what we now call galaxies. However, it wasn't until the 20th century that humanity's comprehension of the universe exploded with new theories and observational tools. One of the most transformative moments occurred in the 1920s when Edwin Hubble, using the Hooker telescope at Mount Wilson Observatory, demonstrated that the nebulae observed in the sky were actually galaxies outside the Milky Way, and furthermore, that these galaxies were moving away from us, indicating that the universe was expanding. This discovery gave rise to the Big Bang theory, first proposed by Georges Lemaitre, and later developed by scientists like George Gamow, which posited that the universe had a specific beginning, a hot, dense singularity that expanded over time to become the cosmos we observe today. Albert Einstein's theory of general relativity, published in 1915, revolutionized the way we understand gravity, not as a force, but as a curvature of space-time caused by mass and energy. This elegant framework replaced Newtonian physics at cosmic scales and allowed predictions of phenomena like gravitational lensing and black holes. In 1964, the accidental discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson offered strong empirical evidence for the Big Bang, capturing the faint glow of the universe's birth. and providing a cosmic backdrop for future measurements. From this point onward, cosmology entered a golden era. With the launch of satellites like COBE, WMAP, and Planck, astronomers were able to measure tiny fluctuations in the cosmic microwave background, leading to precise estimates of the universe's age, around 13.8 billion years. Composition, roughly 5% ordinary matter, and 68% dark energy, and structure. Meanwhile, the Hubble Space Telescope offered breathtaking views of distant galaxies, nebulae, and deep-field images that peered billions of light years into the past, essentially allowing astronomers to look back in time. One of the most important conceptual milestones was the discovery of dark matter and dark energy, two mysterious substances that seem to dominate the cosmos. First, hinted at by the rotation curves of galaxies and the movement of galaxy clusters, dark matter acts as an invisible glue that holds structures together, while dark energy appears to be driving the accelerated expansion of the universe. Despite being undetected directly, their influence is observable and measurable, reshaping models of cosmic evolution. The introduction of quantum mechanics in the early 20th century also influenced cosmology, leading to speculative but intriguing ideas such as quantum fluctuations giving birth to the universe, the concept of inflation, rapid exponential expansion in the first tiny fraction of a second after the Big Bang, and even the possibility of a multiverse, where our universe might be just one of countless others, each with its own laws of physics. These theories remain under investigation, but they illustrate the imaginative and mathematical depths to which human understanding has reached. Milestones in space exploration paralleled and often accelerated our cosmological knowledge. The launch of Sputnik in 1957 marked the beginning of the space age, followed by Yuri Gagarin's historic flight in 1961 and the Apollo moon landings, which culminated with Apollo 11 in 1969. These missions proved that humanity could reach beyond Earth, and though they were largely political in motivation, they yielded valuable scientific data. Later missions, like the Voyager probes launched in 1977, began a long journey to interstellar space, providing first-hand measurements of the outer solar system and the edge of the heliosphere. More recently, spacecraft like New Horizons, which flew past Pluto in 2015, and the James Webb Space Telescope, launched in 2021, have opened new windows into planetary science and deep space observations, allowing humanity to study exoplanets, early galaxies, and the atmospheres of worlds that may one day host life. These endeavors reflect not only technological mastery, but also a deepening curiosity about our place in the universe. The concept of the observable universe ties together many of these threads, offering a framework for what we can actually see and measure. Because light travels at a finite speed, and the universe has a finite age, we are limited to observing a spherical region centered on Earth, roughly 93 billion light-years in diameter, even though the universe may extend far beyond this horizon or may be infinite. This observable limit is not a boundary of the universe itself, but rather a limit imposed by time and the speed of light. Beyond this cosmic horizon lie regions of space forever inaccessible to us, no matter how advanced our technology becomes. Within the observable universe, however, lies a stunning diversity of structures, from stars and planets to quasars, pulsars, and massive galactic clusters interconnected by vast filaments of dark matter in a web-like pattern called the cosmic web. These structures formed through billions of years of gravitational evolution, seeded by tiny quantum fluctuations stretched to macroscopic scales during inflation, and their arrangement reflects the history of cosmic expansion, the influence of dark energy, and the subtle curvature of space-time. Humanity's understanding of the universe has evolved from myths etched in stone to equations etched in photons. From thinking the stars were holes in a firmament to measuring the rotation curves of galaxies and pondering the shape of space-time itself, our journey has been marked by leaps in logic, technology, and sheer imagination. Each discovery has redefined not just what the universe is, but what it means to be a thinking species on a small rocky planet, orbiting an ordinary star, in a galaxy among billions, yet capable of understanding, theorizing, and even reaching out to touch the stars. The historical arc of cosmology reveals a growing humility alongside growing ambition. We know more than ever, yet we are more aware than ever of what we do not know. We have mapped the sky, counted the stars, and deciphered the spectrum of ancient light. But the greatest frontier may still lie ahead, not just in exploring what lies beyond the solar system or even the galaxy, but in understanding the principles that govern the totality of existence. In that pursuit, humanity continues to push the limits of perception, driven by wonder, curiosity, and the deep, unshakable urge to ask, what lies beyond, and what does it mean for us here, on this pale blue dot? You look up at the night sky, and for a moment, everything stops: the noise of life, the stress, the routine, the deadlines, and you're just there, suspended between the dirt beneath your feet and the infinite above your head. It's in this silence that something ancient stirs inside you, a feeling that's hard to name, something between awe and longing, a deep emotional pull toward the stars and the space beyond them. Because whether we admit it or not, every one of us has asked the question, what's out there? It's a question as old as humanity itself, a whisper passed down through generations, spoken in different tongues but always carrying the same yearning to understand our place, to find meaning, to know whether the universe is empty or alive, whether we are alone or part of something unimaginably vast. People should care about what lies outside the solar system, not just because it's scientifically important, but because it touches something emotional and profound, something at the core of what it means to be human. This isn't just about planets and stars. It's about identity, mortality, purpose. The universe doesn't need us, but we need it. We need the mystery, the wonder, the perspective it gives us. Because without it, our problems feel too big, and our lives feel too small. There's a unique kind of fear that comes with thinking about the cosmos, fear not of monsters or darkness, but of scale, of the idea that we are microscopic compared to the universe around us. It's humbling to know that the Earth is a pale blue dot in a sea of blackness, orbiting a small sun in a quiet suburb of the galaxy, and that our galaxy is just one of hundreds of billions, all swirling in a cosmic dance that's been going on for over 13 billion years. There's a fear in knowing that no matter how loudly we shout, our voices may never be heard beyond the faint radio signals leaking from our atmosphere. And yet in that fear, there's also beauty, a strange, aching kind of beauty, the kind that poets and dreamers have tried to capture for centuries. We fear the void, but we are drawn to it. We fear our smallness, but we seek to transcend it. That paradox lies at the heart of why the cosmos moves us. It's not just a physical space we want to explore. It's a psychological one, a mirror that reflects our hopes, our fears, our questions, our desire to be part of something more. Children feel it naturally. They look at the stars and ask if aliens exist, if spaceships can go to other galaxies, if time travel is possible. That's not just curiosity, it's the first stirring of existential awareness. It's the mind reaching beyond the boundaries of home and safety into the unknown, because something inside us is wired to wonder. That wonder doesn't die. As we grow older, it just gets buried under responsibilities and distractions. But every once in a while, it breaks through. When we see a photo of a galaxy millions of light years away, or hear that a new Earth-like planet has been discovered orbiting a distant star, and suddenly we remember, we are explorers. It's in our nature. From crossing oceans to climbing mountains to decoding the human genome, our story has always been about pushing limits, and space is the ultimate limit. Not because we can conquer it, but because it challenges us to grow, to innovate, to think in longer timelines and larger scales, to imagine a future where our descendants look back at Earth not as a prison, but as a birthplace. Caring about what lies outside the solar system also connects us to each other. The stars belong to no nation, no ideology, no religion. They are universal. When we look up, we all see the same sky, and in that shared gaze, there is unity, a reminder that we are all riding the same fragile planet through an indifferent universe, and that maybe, just maybe, our differences matter less than we think. In the face of the cosmic void, the petty divisions of daily life fade. You start to think less about who's right and more about what's right. You think about future generations, about sustainability, about stewardship. You begin to see Earth as an oasis worth protecting, not just for us, but as the only known haven of life in a universe still silent and unexplored. This shift in perspective is called the overview effect, reported by astronauts who've seen Earth from orbit and felt a profound sense of connection, responsibility, and love for humanity. It's an emotional transformation, and it's contagious. The more people learn about space, the more they care about life, about preserving it, expanding it, understanding it. There's also something deeply personal in the cosmic question. It forces us to face our own mortality, our own insignificance, but also our potential. We realize that we are temporary, but we're also part of a continuum. The atoms in our bodies were forged in stars billions of years ago. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it was cooked in the hearts of massive suns that lived and died long before Earth formed. You are, quite literally, made of star stuff, as Carl Sagan once said. And that's not poetry, that's physics. There's something emotionally overwhelming about realizing that you are the universe, becoming aware of itself. That your thoughts, your dreams, your memories all arise from particles and forces born in the Big Bang. To study the universe is to study yourself, to peel back layers of reality and find not just cold equations, but meaning. Maybe not objective meaning, but existential meaning, the kind that comes from connection, from understanding, from being part of a larger story. When we think about space, we often focus on the technological rockets, telescopes, simulations, but behind every line of code, every launch, every calculation, there are people with a spark in their eyes, chasing something they can't fully explain. It's not just data they want, it's transcendence. They want to be part of something that outlives them. They want to contribute to a human legacy that reaches the stars. And isn't that what we all want in some way? To matter? To be remembered? To leave something behind that proves we were here, that we tried, that we reached? The cosmic journey isn't about escapism. It's about elevation. It's about saying, this is who we are, not just consumers, not just workers, not just survivors, but thinkers, creators, explorers, beings who looked into the dark and refused to be afraid. The emotional connection to the unknown is not weakness, it's strength. It's the fuel that powers science, the passion that sustains inquiry, the wonder that makes education meaningful. People care when they feel, and space makes us feel hope, fear, love, awe, grief, joy. It reminds us that we are temporary but not meaningless, that we are small but capable of great things, that the universe doesn't owe us answers, but we are worthy of seeking them anyway. That even in a cosmos filled with silence, the act of asking a question is itself a kind of music, a way of pushing back against the dark. And maybe that's the ultimate emotional truth of why space matters, because it gives us a reason to dream. In a world often dominated by bad news and short-term thinking, space invites us to look up, to think long-term, to build for the future, to imagine a day when humanity spreads beyond Earth, not to escape our problems, but to honor our potential. To be curious is to be alive. To care about what lies beyond the solar system is to care about possibility itself. To say that we are not finished yet, that the best chapters of our story might still be unwritten, floating out there in the stars, waiting for someone to care enough to go find them. What if everything you thought you knew about reality was only a sliver of a greater truth? A tiny fragment glimpsed through the narrow keyhole of our solar system. And what if just beyond that threshold, beyond the cold outer rim of our planetary neighborhood, lay secrets that could rewrite everything from our understanding of physics to the origins of consciousness itself? What lies outside the solar system is not just a scientific inquiry, it is a gateway to confronting the deepest philosophical and existential questions we can ask. And it's a conversation that demands your participation, because the search for what's beyond isn't something reserved for astronomers and physicists alone. It belongs to all of us. It's an open invitation to wonder, to imagine, to debate, and to question. What if you woke up one morning to the news that a planet had been found orbiting a nearby star with unmistakable signs of life in its atmosphere? How would that change the way you look at the sky, at your own life, at the place we call home? Would Earth still feel like the center of your universe? Or would you suddenly feel like part of a much larger, unfolding cosmic story? This mystery affects us in ways most people don't even realize. It quietly reshapes our philosophies, our religions, our sense of purpose. If the universe is teeming with life, what does that say about humanity's uniqueness? If it's empty, what does that mean for our role as conscious observers in a silent cosmos? Every discovery of a new exoplanet, every measurement of cosmic radiation, every signal or silence tilts the balance in these questions. And the thing is, we're not passive spectators in this exploration. Our generation is actively shaping the next chapter of cosmic discovery. We are building the instruments, programming the algorithms, sending the spacecraft, asking the questions. That means we also carry the responsibility of how we interpret what we find. Will we be humble in the face of the unknown? Or will we try to bend it to fit our existing beliefs? Will we use our discoveries to inspire cooperation across nations and cultures? Or to draw new lines of division? These aren't theoretical debates. They are the moral and intellectual challenges of a civilization that's reaching for the stars. So ask yourself, what do you believe is out there? Do you think life is common or rare? Do you think the universe has a purpose, or is it all random? Do you think we're meant to explore beyond our solar system, or should we focus on Earth alone? There are no right answers, but the act of asking is itself transformative. When you start thinking on a cosmic scale, everything shifts. Petty worries seem smaller. Big ideas seem possible. You begin to see yourself not just as a citizen of a country, but of a planet. Not just as a temporary being, but as part of a long lineage that might continue far into the future if we survive, if we grow, if we care. Because let's not pretend the unknown is comfortable. It's not. It's intimidating. It challenges our assumptions, disrupts our models, forces us to admit that we don't know everything. But isn't that the point of exploration? To face the unknown not with fear, but with courage? To recognize that uncertainty is not something to hide from, but something to lean into. Because it's only in the unknown that true growth can happen. Think about how far we've come in just the past century. 100 years ago, we didn't even know there were other galaxies. Now, we've mapped billions. A few decades ago, the idea of exoplanets was speculative. Now we've discovered thousands. Each time, the universe has turned out to be bigger, older, and stranger than we thought. So, what will we discover next? Will we find biosignatures in the atmosphere of a nearby exoplanet? Will we detect a technosignature artificial signal from a distant civilization? Will we uncover new forms of matter or energy that solve the mystery of dark matter? Will we confirm that time and space behave differently in certain corners of the universe, pointing toward the existence of wormholes or other dimensions? These aren't fantasies. They're active areas of research, and any one of them could redefine what it means to be human. And the beauty is, you don't have to be a scientist to be part of this revolution. You just have to care. You just have to ask the questions, share the ideas, join the conversations, start discussions with friends about the universe. Ask them what they think is out there. Watch a space documentary together and talk about how it made you feel. Follow missions like James Webb or Voyager or the upcoming LUVOIR telescope. Read about the search for life on Europa or the moons of Saturn. Explore citizen science projects that let you help classify galaxies or hunt for exoplanets from your own device. Ask your teachers or mentors about the Big Bang, or quantum fields, or cosmic inflation. Let your curiosity run wild, because every question asked is a spark, and enough sparks make fire. The future of our understanding of the universe isn't just built in labs or observatories. It's built in living rooms, in classrooms, in message boards, in conversations that begin with someone saying, "Have you ever wondered?" That's how movements start. That's how ideas evolve. That's how a planet of individuals becomes a species that thinks in galaxies. And don't let anyone tell you this stuff doesn't matter. It matters more than most things, because the way we see the universe shapes the way we see ourselves. If we believe the cosmos is cold and dead, we risk becoming cold and numb. But if we see it as mysterious and alive with possibility, we stay open, curious, empathetic. We stay willing to ask the big questions, to connect with others, to strive for better. The unknown isn't just out there, it's in us too. Every person is a universe of thoughts, emotions, dreams, and memories. And just like the cosmos, we each contain both the known and the unknowable. To explore the stars is to honor both. To seek new worlds is to affirm that discovery is still possible not just in science, but in spirit. That wonder is still worth pursuing. That in a time when so much feels fragmented, there's still a horizon we can reach for together. So what do you think lies beyond the solar system? Not just in terms of physics and stars and space, but in terms of meaning, of emotion, of potential. Do you feel a sense of peace when you look at the stars or anxiety? Do you believe the universe is trying to tell us something? Is it we who give it meaning by trying to understand it? These aren't rhetorical questions. They're invitations to think, to feel, to share. Because in the end, the cosmos is not just out there, it's in every question we ask, every story we tell, every discovery we make. And maybe the most important discovery waiting out there isn't a new planet or a new law of physics. Maybe it's a new way of seeing ourselves, a new kind of connection, a deeper appreciation for the miracle that we're here at all. Asking these questions, building these dreams, looking up instead of down. This isn't just science. This is the future of human consciousness. This is the next chapter of our story. And the best part is, you're already part of it. You always have been. You just have to look up, ask the question, and join the search. Because what lies beyond the solar system isn't just a mystery waiting to be solved. It's a conversation waiting to begin. Far beyond the pale halo of our solar system, past the icy outposts of the Kuiper Belt and the lonely orbit of the last known dwarf planets, lies a realm so vast, so quiet, and so ancient that the mind struggles to grasp its immensity. It begins at the outer edge of the heliosphere, where the breath of the Sunday fades into the silence of interstellar space, and from there, the universe unfolds into a staggering ocean of stars, dust, and mysteries older than time itself. Imagine standing at the edge of everything you've ever known, staring out into the interstellar void, surrounded not by silence, but by the soft whisper of radio waves, the distant echo of dying stars, the invisible hum of gravity, and the slow dance of galaxies through a fabric that stretches, bends, and pulses with energy unseen. Space is not still. It is a living cathedral of movement, creation, and collapse. It is a stage on which cosmic phenomena perform in cycles so immense that our entire history as a species fits into the blink of a galactic eye. This is not just outer space. This is the beyond an atmosphere not made of air, but of wonder. As your mind drifts through the void, the scale becomes overwhelming. You pass by rogue planets, frozen worlds unmoored from any star, drifting alone in eternal night, their cores possibly still warm from the chaos of their ejection, harboring subsurface oceans and strange, isolated chemistries. Then come the stellar nurseries great, billowing clouds of gas and dust, glowing with ultraviolet light, where stars are born from gravitational collapse, igniting nuclear fusion in brilliant flashes that cut through the darkness like the first spark in a forge. You float by stars of all kinds, burning red dwarfs that will outlive everything else, massive blue giants doomed to short, luminous lives, and collapsed corpses of stars, white dwarfs glowing like embers, neutron stars spinning with deadly precision, and black holes so dense that not even light escapes their grasp, warping time and space around them into spirals of darkness. You watch galaxies swirl like cosmic hurricanes, arms spiraling with stars, gas, and gravity, colliding and merging in slow-motion crashes that send ripples through the structure of the universe itself. Between these great islands of light lie the cosmic void's enormous expanses of near-nothingness, regions where matter is so sparse that an entire galaxy might drift for millions of years without meeting another. These voids are not empty, however, they are charged with potential, humming with the residual energy of the Big Bang, gently influenced by the invisible architecture of the universe. Dark matter. This enigmatic substance does not emit light or radiation. It cannot be touched, seen, or smelled. Yet it makes up about a quarter of the universe, exerting gravitational pull that shapes galaxies, stabilizes clusters, and maps out the great filaments of the cosmic web, the vast interconnected structure of the universe that resembles a neural network or the roots of an ancient interstellar tree. Even more mysterious is dark energy, the force that drives the acceleration of the universe's expansion. It pushes galaxies apart faster and faster, hinting at a future where all lights will vanish beyond the observable horizon, leaving a universe that seems lonelier by the second. Amid this grandeur, key players in cosmology work tirelessly to decode the language of the stars. Theorists and observational astronomers alike stare into telescopes and equations, piecing together the story of the cosmos from fragments of light and fluctuations in temperature. Figures like Albert Einstein laid the foundation with general relativity, describing gravity not as a force but as a bending of space-time. Georges Lemaitre proposed the expanding universe. Edwin Hubble confirmed it with his redshift observations, opening the door to the Big Bang theory. More recently, scientists like Vera Rubin confirmed the presence of dark matter through galactic rotation curves, while teams behind spacecraft like WMAP and Planck mapped the cosmic microwave background, giving us a snapshot of the universe when it was just 380,000 years old. Meanwhile, telescopes like the Hubble Space Telescope and its successor, the James Webb Space Telescope, peer into deep time, capturing ancient light from galaxies formed shortly after the dawn of creation. Researchers like Kip Thorne and Roger Penrose pushed the boundaries of black hole physics and gravitational waves, and scientists at LIGO and Virgo finally detected those waves in 2015, a cosmic vibration that confirmed predictions made a century earlier. Even as these intellectual giants reshape our understanding, the tone of cosmic exploration remains defined by awe. Scientific curiosity here is not sterilate, is reverent, emotional, restless. It is the beating heart of a species that builds machines to touch the stars while lying awake at night, asking what it all means. It is the spirit that sent Voyager 1 into interstellar space with a golden record, a time capsule of human thought, sound, and emotion, now drifting silently through a dark ocean where no human eye may ever see it again. It is the drive that fuels international collaborations like CERN and NASA, the European Southern Observatory, and countless university labs that test the edge of what can be known. It is found in the child who points at the stars and asks, "What's out there?" and in the engineer who spends her career calculating trajectories that carry robotic explorers past Saturn's rings and into the unknown. The atmosphere of the cosmos is not merely made up of cold particles, and radiation it is steeped in story. Every light you see in the sky is a history book. Every pulsar is a clock. Every shadow is a clue. The cosmos is not indifferented, is layered, reactive, filled with energy flows and gravitational dances that echo across eons. Supernovae scatter the elements of life into surrounding space, seeding clouds that will form new solar systems. Gamma-ray bursts erupt with more energy than 1 billion suns in seconds, illuminating the ends of stars and the violence of creation. Quasars, the brilliant hearts of early galaxies, shine with the power of matter falling into black holes, marking the places where galaxies once blazed and grew. And in the quiet in-between, neutrinos pass through entire planets as if they weren't there, while cosmic rays travel at near-light speeds, colliding with our atmosphere and reminding us that space is always, in some subtle way, in contact with us. To immerse yourself in the atmosphere of the universe is to surrender your ego to the immensity of what exists. It's not about feeling small, it's about feeling connected. You are made of the same atoms that built the stars. The carbon in your cells, the iron in your blood, the oxygen in your lung sol were born in ancient supernovae. You are a temporary configuration of cosmic elements arranged by time and chance into a being that can ask questions about its origins. And while your life may last only decades, the atoms within you will continue their journey through soil, water, air, perhaps one day into space itself. You are a fleeting consciousness riding on an eternal wave of matter and energy, shaped by physical laws that extend beyond the solar system into the deepest reaches of the cosmos. The tone of this setting is not science fiction, it is scientific reality painted in strokes of wonder. The galaxies are real, the voids are real, the dark matter is real, and the curiosity that drives us is real. But there are still so many questions. What is dark energy? What came before the Big Bang? Are there other universes? Will time eventually stop or loop? Will we ever escape the bounds of our own galaxy? Are we truly alone? Or simply one voice in a chorus too vast to yet detect? These questions are not trivial. They are fundamental. They guide the development of new technologies, the formulation of new physics, the reshaping of old ideas. They inspire art, literature, philosophy. They stir dreams. They build futures. So when we talk about building an atmosphere around what lies beyond the solar system, we're not just describing a place, we're invoking a feeling, a sense of motion, of inquiry, of reverence, a place where knowledge meets the edge of mystery and where every answer deepens the questions, a place where science doesn't destroy wonder, but magnifies it, a place where we are not just spectators, but participants in a vast, ongoing experiment called existence, a place where looking outward becomes a way of looking inward. The stars are not just out there, they are in us, in our stories, in our questions, in our courage to seek the unknown. And in that, the cosmos becomes more than a destination. It becomes a mirror, a teacher, a home. As we stand on the fragile edge of human knowledge, gazing into the depths of the universe with instruments crafted from our ingenuity and fueled by our relentless curiosity, we begin to sense that something may always remain just out of reach, that perhaps, no matter how far we push, the true edge of the universe may forever elude us. It is not simply a matter of distance, nor of scale, but of the very nature of reality itself. The universe, as we currently understand it, is expanding, but not into anything. There is no edge in the traditional sense, no cosmic wall we can find and mark as the boundary. The observable universe, limited by the speed of light and the age of the cosmos, is only a portion of a potentially infinite or unknowably larger whole. Beyond what we can see lies a realm that is causally disconnected from USAs from which light has not had time to reach us, and never will if the acceleration of the universe continues unchecked due to dark energy. This cosmic horizon is a fundamental constraint, an unbreakable wall of time and physics, suggesting that our knowledge of the totality of the universe will always be incomplete, a haunting foreshadow of eternal mystery. The seeds of this conflict are deeply embedded in the physics we rely on. At the smallest scales, quantum mechanics describes a universe governed by probability, uncertainty, and strange dualities, particles that are waves, actions that are not determined until observed. At the largest scales, general relativity describes gravity as the curvature of spacetime, smooth and continuous. Both frameworks are astoundingly successful in their domains, yet fundamentally incompatible. When we try to merge them into a single, unified theory of quantum gravity, paradoxes emerge. Time itself becomes ambiguous. Space may be emergent rather than fundamental. Concepts like cause and effect begin to blur. Black holes, once thought to be the perfect embodiment of gravitational collapse, turn into battlegrounds of contradiction, places where the rules break down and information may be lost, challenging the bedrock principle of unitarity in quantum mechanics. Stephen Hawking's information paradox still looms unresolved, and though developments like holography and the AD-S CFT correspondence offer tantalizing hints, they have not yet yielded a complete picture. These paradoxes are not academic. They are signs that our current understanding, as elegant and powerful as it is, may be only a shadow of a deeper, stranger truth. Even our observational capabilities, astonishing as they are bounded. Every telescope, no matter how advanced, is limited by the speed of light, the sensitivity of its detectors, the opacity of certain cosmic eras, and the interference of foreground noise. We cannot see beyond the surface of last scattering the moment 380,000 years after the Big Bang, when the universe became transparent to light. Before that, the cosmos was a hot, dense plasma opaque to photons. Our only window into this earlier time comes through gravitational waves or neutrinos, both incredibly hard to detect and interpret. Moreover, the light we do receive from the distant universe is redshifted, stretched into longer wavelengths by cosmic expansion, until it becomes so faint and diffuse that it blends with the background. Eventually, as the expansion accelerates, more galaxies will move beyond our cosmic event horizon, their light unable to ever reach us. In billions of years, even the nearest galaxies will fade from view, and future astronomers may see only the ghost of what we now know, believing their galaxy to be all that exists. This is not hypothetical. This is the future written into the math of dark energy and expansion. As we search deeper into the structure of the cosmos, we confront more puzzles. Why is the universe so flat? Why did inflation happen? And what caused it to start or stop? What is dark matter made of? Why does the cosmological constant, the energy density of empty space, have such a small but non-zero value? These aren't minor technicalities. They are fundamental cracks in the edifice of cosmology, signs that we are missing key pieces of the puzzle. The cosmic microwave background, once hailed as the perfect confirmation of the Big Bang, contains slight anomalies in temperature distribution that hint at unknown physics. Measurements of the Hubble constant, the current rate of expansion differ depending on how we measure them, suggesting either unknown systematic errors or new physics entirely. Each new discovery adds another layer to our understanding, but also reveals how fragile that understanding truly is. The more we know, the more we see the outlines of what we don't. Foreshadowing the limits of human comprehension is not an admission of defeat, it is a recognition of the scale and strangeness of the universe we inhabit. If space is not infinite, what lies beyond its boundary? If time had a beginning, what came before? If the universe is part of a multiverse, with other realms governed by different laws of physics, can we ever observe them? Or are they forever hidden behind a veil of cosmic censorship? The multiverse theory, while mathematically possible, may never be testable. It raises epistemological questions about what counts as science, about whether we can accept truths that we cannot verify. This tension between the knowable and the unknowable is the essence of the conflict ahead. The closer we get to the edges of the observable universe, of mathematical possibility, of conceptual comprehension, the more resistance we encounter. It is as if the cosmos teases us, offering answers wrapped in new enigmas, guiding us forward only to reveal another wall, another limit, another impossibility. Human biology, too, is part of the problem. Our brains evolved to navigate a world of meters and seconds, not light years and eons. We can simulate other dimensions on supercomputers, but we cannot truly imagine them. We can describe quantum fields with equations, but we cannot intuit their behavior the way we understand falling apples or flowing rivers. Our instruments extend our senses. Our mathematics extends our logic, but we remain tethered to a narrow window of reality, one that may not be equipped to perceive or process what truly lies beyond. Artificial intelligence and machine learning may help us navigate some of these boundaries, discovering patterns we cannot see, deriving equations we cannot conceive. But even then, the final step, meaning, must still be taken by a mind capable of reflection and awareness. The limit is not just in the starset, is within us. And yet, for all these signs, we continue. We build bigger telescopes, collide particles at higher energies, invent theories that twist the fabric of reality into multi-dimensional strings and holographic surfaces. We map the voids, catalog the galaxies, watch for the flicker of life on distant worlds. We refuse to stop. Why? Because the very act of confronting the edge, even an edge, we may never crosses what makes us human. We are not discouraged by limits. We are inspired by them. The conflict between what is known and what lies forever beyond is not a failure of science, it is its driving force. Every paradox, every constraint, every unanswered question is a torch in the dark, illuminating the shape of the unknown. It tells us that there is still more to seek, more to learn, more to imagine. So what if we never find the true edge of the universe? What if the cosmos is not only bigger than we think, but stranger than we can think? That possibility should not bring despair, it should bring wonder, because it means that no matter how far we go, there will always be another mystery to unravel, another horizon to chase. The universe is not a puzzle to be completed. It is a symphony to be explored, one movement at a time, one question after another, forever echoing through the minds of those who dare to ask. The edge is not a place. It is a process, a challenge, a calling. And it is already shaping the next generation of explorers, thinkers, and dreamers who will stand where we stand and ask, with fresh eyes and fearless hearts, what lies beyond this? At the heart of modern cosmology lies a persistent, unresolved conflicta grande tension, not of politics or personalities, but of ideas, models, and the very fabric of reality. It is the conflict between competing scientific theories that each attempt to explain the structure, origin, and fate of the universe, yet diverge on critical points like whether space is infinite or finite, whether time had a beginning or is emergent, and whether we will ever be able to define or even comprehend what lies at the edge of existence. These tensions are not minor disagreements over data interpretation. They are deep philosophical and mathematical chasms within our understanding of the cosmos, gaps between what we observe and what our most elegant theories predict. Cosmologists stand at the intersection of these contradictions, striving to reconcile the expanding database of observational evidence with models that either fracture under scrutiny or spiral into speculative abstraction. And nowhere is this struggle more evident than in the question of the universe's edge. Does it exist? Can it be defined? Or is it a mirage conjured by our limitations? A boundary that recedes the closer we get. The Big Bang Theory remains the dominant cosmological model, supported by overwhelming observational evidence, most notably the cosmic microwave background radiation, the redshift of distant galaxies, and the large-scale structure of the universe. According to this model, the universe originated from an extremely hot, dense state approximately 13.8 billion years ago, and has been expanding ever since. Yet this expansion does not occur into pre-existing space. Rather, space itself stretches, carrying galaxies away from each other. Here, the intuitive idea of an edge quickly begins to break down. If the universe is infinite, as some models suggest, then there is no edge, just more space extending in every direction, forever. But if the universe is finite, then it must somehow curve back on itself, like the surface of a sphere, allowing you to travel in a straight line and eventually return to your starting point. In such a model, space has no edge. Either it is boundaryless, like the two-dimensional surface of a planet, but embedded in higher dimensional geometry. This dualifinite but unbounded creates a paradoxical vision of the universe that is mathematically sound yet conceptually difficult to grasp. At the core of this conceptual battle is the nature of space-time itself. General relativity offers a geometric interpretation of gravity and provides a robust framework for understanding large-scale structures, black holes, and cosmic expansion. However, it says little about the quantum-scale fabric of the early universe, where energy densities are extreme and time itself may lose its classical meaning. In contrast, quantum mechanics governs the small and the uncertain, describing reality in terms of probabilities and superpositions. But when quantum effects are applied to gravity, especially near the supposed beginning of the universe, contradictions erupt. Attempts to unite these theories, such as string theory and loop quantum gravity, produce wildly different pictures of reality. In string theory, the universe may exist in 10 or 11 dimensions, with our familiar four-dimensional spacetime being a projection or surface of a higher dimensional bulk. Some versions of string theory support the idea of a multiverse, an ensemble of bubble universes, each with different physical constants, some finite, some infinite, none directly observable. Loop quantum gravity, on the other hand, replaces continuous spacetime with a granular, quantized structure and predicts that the Big Bang may not have been a beginning at all, but a bounce from a previous contracting phase. These models each offer tantalizing solutions but lack definitive empirical proof, creating a philosophical and scientific clash over what the universe truly is. Observational evidence, while rich and increasingly precise, does not always resolve these conflicts. In fact, it often deepens them. The Hubble tension is one of the most prominent examples. Two primary methods exist to calculate the rate of cosmic expansion. One based on observations of nearby Type Ia supernovae and Cepheid variables, which suggest a higher value, and the other based on measurements of the early universe through the cosmic microwave background, which suggest a lower value. Despite improved precision, the gap between these values has not narrowed, leading to the possibility that new physics, perhaps involving dark energy, exotic particles, or modifications to gravity, is needed. But such changes ripple through the entire framework of cosmology, potentially altering the inferred age, size, and shape of the universe. Similarly, dark matter and dark energy, which together account for 95% of the universe's total mass energy content, have not been directly detected. Their presence is inferred from gravitational effects and cosmic acceleration, but what they are remains a mystery. Every model that includes them must contend with this observational gap, balancing explanatory power against empirical emptiness. In parallel, the philosophical interpretation of these models diverges. The infinite universe appeals to the mind that favors mathematical elegance and philosophical simplicity in unending cosmos, with no privileged location or special boundary. Yet it also introduces paradoxes. If the universe is infinite and matter is uniformly distributed, then every possible arrangement of atoms must occur somewhere an infinite number of times. Somewhere out there, an exact duplicate of you may be living a parallel life, reading this exact same sentence in an identical copy of Earth, with another version of this debate playing out under a different sky. Some physicists find this idea thrilling, while others find it scientifically empty, a consequence of mathematical extrapolation with no testable implications. The finite universe, by contrast, seems more grounded, but it demands explanations for the nature of its closure. What lies beyond the curvature? How does space fold without an embedding dimension? These questions spark debate over whether the universe is something we can ever truly model in full, or whether our frameworks are approximations, useful maps, but not the territory. The struggle to define the edge of the universe is also a struggle with language and human cognition. Our brains evolved to comprehend objects, surfaces, and volumes, not n-dimensional manifolds and relativistic horizons. When we imagine the edge, we picture cliffs, walls, ends. But the universe may not have any of these. It may be a mathematical object that cannot be visualized, only described through equations. For example, in the inflationary model, the universe underwent an exponential expansion in its first fraction of a second, smoothing and flattening space to such an extreme degree that its geometry appears Euclidean, even if it is globally curved. This rapid inflation also suggests that what we observe is just a tiny patch of a much larger inflating field dome that may continue endlessly in other regions, producing pocket universes through quantum fluctuations. This is the so-called eternal inflation model, which again points toward a multiverse. But critics argue that such models are untestable, and therefore unscientific. Without observable signatures, are we studying physics or metaphysics? The observational frontier itself is constrained by the nature of light, time, and cosmic evolution. We can only see as far as light has had time to travel since the universe became transparent. Beyond the surface of last scattering, light cannot inform us. We must rely on indirect signatures like primordial gravitational waves, which are faint and incredibly difficult to detect. Even within the observable universe, we see the past, not the present. The galaxies at the edge of our field of view are not as they are today, but as they were billions of years ago. This introduces another kind of edge, not spatial, but temporal. We live inside a four-dimensional light cone, and beyond it lies not darkness, but unknowability. As the universe accelerates, galaxies will vanish over the horizon, their light forever out of reach. Even now, the majority of the universe is inaccessible, expanding faster than light can catch up. The more we understand cosmic acceleration, the clearer it becomes that a true physical map of everything is impossible. The universe is not only expanding, it is slipping away. Cosmologists, then, operate in a space of both triumph and torment. They have built a standard model of cosmology, CDM, lambda cold dark matter, that fits a vast array of data with remarkable accuracy, yet they also know it is incomplete. It doesn't unify gravity with quantum mechanics. It doesn't explain dark matter or dark energy. It doesn't resolve the singularity at the beginning of time. And it doesn't tell us what lies beyond the edge, or whether that edge is even a meaningful question. Some researchers believe we are on the cusp of a revolution, like the one that replaced Newtonian mechanics with relativity, or classical physics with quantum theory. Others argue that we are hitting the limits of human comprehension, that certain truths about the universe may be forever beyond our grasp, not because they are too complex, but because they are fundamentally inaccessible. The universe is not required to reveal itself in ways that are convenient to us. This conflict, the tension between models, between the observable and the theoretical, between what we can test and what we can imagine, is not a flaw in science. It is science. It is the engine that drives inquiry, the crucible in which new ideas are forged. But it also carries weight. It reminds us that we are creatures of limited perception, using finite tools to study an infinitier, perhaps just ungraspable reality. It warns us that our best ideas may be wrong, or incomplete, or right only in narrow regimes. It humbles us, and it excites us. Because the edge of the universe, whatever it may be, is not just a boundary of space, it is the edge of understanding. To stand at that edge is to confront the unknown with courage, to admit what we do not know, and to press forward anyway. The conflict may never be resolved, but in its very struggle lies the essence of discovery. If the universe truly has no edge, no boundary, no wall, no outer shell separating what exists from what does not, then we are forced to abandon some of our deepest intuitions about space, scale, and meaning. The absence of an edge is not simply a scientific curiosity. It is a foundational shift that ripples through every layer of understanding we have about the cosmos and our place within it. For centuries, the human mind has searched for borders, the edge of the map, the edge of the ocean, the edge of the sky. An edge implies limit, and a limit implies structure. But if the universe is infinite or closed upon itself in such a way that it has no edge, we are staring not at a container of reality, but at a seamless, unending fabric. And in doing so, we confront a radical redefinition of what the universe is, how it began, what laws govern it, and whether we can ever hope to understand it in full. The consequences of this conceptual rupture are enormous. It reorients the entire framework of cosmology, demands new physics to explain an edgeless existence, and triggers deep philosophical and existential questions that extend beyond the reach of science alone. From the standpoint of physics, an edgeless universe upends several assumptions. First, it challenges the idea of boundary conditions, which are essential to solving the equations of general relativity and quantum field theory. In a finite, bounded system, we can use these edges to constrain variables, define volumes, and understand the behavior of energy and matter over time. Without an edge, we must turn to topological models that describe space as curved or looped in higher dimensional ways. One possibility is that the universe is like the surface of a four-dimensional sphere, finite in volume, but with no boundaries. Another is that it is truly infinite, extending forever in all directions with no repeating structure. Both cases present problem. A finite, closed universe implies that the universe could curve back on itself, but this raises questions about what geometry underlies that curvature and whether it implies extra dimensions we cannot perceive. An infinite universe, meanwhile, leads to difficult paradoxes. An infinite amount of matter, energy, entropy, and even identity. If the universe has no end, then statistically, every possible configuration of matter should occur somewhere, perhaps infinitely many times, including copies of you, this Earth, and even this very moment. This thought leads straight into the heart of the philosophical implications. What does it mean to live in a universe without an edge? What does it say about the uniqueness of our experience, of our planet, of our consciousness? In a bounded universe, we might imagine ourselves in a finite system, subject to discoverable laws and comprehensible mechanisms. But in an infinite or edgeless cosmos, meaning itself becomes difficult to define. Are we significant in a universe that never ends? Does our story matter if it is repeated endlessly in distant regions? This line of thought touches the core of existential philosophy. For millennia, religions, myths, and cultures have placed humanity within some cosmic boundary, beneath a dome, atop a disk, orbiting a sun, within a galaxy. Each step in scientific discovery has pushed that boundary farther out. But to declare there is no boundary at all is to pull the rug out from under the last illusion of centrality. It renders us not merely small, but unanchored. And yet, paradoxically, this realization can also be liberating. If there is no edge, then there is no final limit to exploration, knowledge, or imagination. We are not confined. We are free to explore an unending sea of possibilities. Such a cosmos demands new physics. Our current models based on general relativity, quantum mechanics, and the standard model of particle physics work well within local domains, but they struggle at the extremes, at the singularities of black holes, at the earliest moments after the Big Bang, at the cosmic scale where dark energy dominates. These models assume smooth space-time, predictable symmetries, and known particles. But an edgeless universe may not obey those assumptions. It may contain topological features we have not yet observed, fields we have not yet discovered, and dimensions we cannot yet perceive. The unification of quantum mechanics and general relativity remains one of the greatest challenges in theoretical physics. Candidates like string theory and loop quantum gravity aim to provide a deeper, more complete description of reality in which space and time are emergent properties, not fundamental ones. In such frameworks, the notion of an edge may be replaced with entanglement surfaces, information boundaries, or even holographic principles that treat the universe not as a three-dimensional space, but as a projection from a deeper layer of reality. These models are not only mathematically exotic, they are philosophically radical, suggesting that space, time, and matter as we experience them are not the base layer of existence, but a simulation-like phenomenon arising from deeper informational structures. The absence of an edge also influences the concept of origin. If the universe has no boundary, then it may have no beginning either, at least not in the way we currently understand beginnings. The classical Big Bang model describes a singularity, a point where density, temperature, and curvature become infinite. But infinities are signs of a theory breaking down, not physical realities. Alternative models propose a bounce from a prior contracting universe, a multiverse landscape where new regions bud off from inflating space, or even a timeless quantum state, from which time and space emerged as decohered possibilities. Each of these models eliminates the need for a singular origin point and instead describes the universe as a self-contained system without external cause. This challenges not only physics but metaphysics. If the universe did not begin, what does creation mean? If there is no edge, what is outside? If there is no outside, then perhaps the question itself is meaningless, revealing the limits not of the universe, but of our language and cognition. The implications stretch into cosmology's deepest mysteries. What governs the large-scale structure of the universe? The cosmic web, a vast network of galaxies, clusters, and voids, suggests that gravity and dark matter have sculpted space into a filamentary pattern. Yet this structure only persists within the observable universe. Beyond our cosmic horizon, we cannot see, cannot test, cannot know. If the universe is infinite, how representative is our visible region? If it's just one bubble in a multiverse, then our laws of physics may be local rules, not universal truths. This undermines the ambition of cosmology as a discipline find a final theory of everything. Instead, we may be discovering a theory of here, a model that works within our observable patch, but which is merely one realization among countless others. This possibility demands intellectual humility. It suggests that even our most precise measurements and successful models may be contingent, not absolute, that the cosmos, in its fullness, may be too vast for any finite mind to grasp. And yet, we try. We build better telescopes. We measure cosmic background radiation with higher resolution. We search for signatures of inflation, for primordial gravitational waves, for exotic particles that might reveal the nature of dark matter. We map the distribution of galaxies to test curvature and topology. We study the polarization of light from the early universe to look for clues of new physics. This relentless pursuit is not blind optimism, it is the essence of scientific integrity. Even in the face of infinite complexity and theoretical ambiguity, we search for clarity. Every new observation narrows the field of possibility. Every anomaly suggests a revision. Every model, no matter how abstract, is a stepping stone towards something deeper. If the universe has no edge, then the journey has no end, and knowledge becomes a direction, not a destination. Philosophically, this endlessness challenges the way we define meaning. In an edgeless universe, there is no central point, no preferred frame, no cosmic throne. We are not at the top of a hierarchy, but embedded in a vast, democratic cosmos. This can be terrifying. It removes the illusion of specialness, but it can also be empowering. We are part of the universe, made from its dust, driven by its laws, illuminated by its light. Our consciousness is not an aberration, but a natural product of complexity, evolution, and time. In a universe without edge, every thought, every act, every discovery is an echo within eternity. There is room for all stories, all meanings, all interpretations. Some may look at the edgeless universe and see nihilism. Others see potential and invitation to participate in the unfolding of a never-ending mystery. For centuries, our understanding of the cosmos expanded slowly, grounded in Earth-based observations and limited by the unaided eye. But the last 100-year infinitesimal flash on the cosmic clock have seen an unprecedented transformation, culminating in a series of turning points that fundamentally reshaped how we perceive the universe. These turning points, driven by key scientific revelations, breakthroughs in technology, and astonishing data from deep space telescopes, did more than just answer questions. They opened doors to new mysteries and set the stage for a deeper, stranger chapter of human exploration. Among these, perhaps none has been more disruptive or consequential than the discovery of dark energy, the mysterious force driving the accelerated expansion of the universe, which has transformed cosmology from a search for origins into a study of destiny. As we crossed this conceptual threshold, everything changed, not just our models of space and time, but our assumptions about what the universe is and how it behaves on the largest scales. The first major revelation came in the early 20th century with Edwin Hubble's observation that distant galaxies are moving away from us, and that the farther they are, the faster they recede. This was the first observational proof that the universe is expanding. Building on Einstein's general theory of relativity, which had already described space and time as a single, dynamic entity that can bend and stretch, Hubble's findings provided empirical weight to the idea of a growing cosmos. What had once been viewed as a static, eternal firmament was now understood to be dynamic, evolving, and deeply interconnected. This singular discovery birthed the Big Bang Theory, the idea that the universe began from a hot, dense state and has been expanding ever since. But while this model explained many features of the observable cosmos, from the abundance of light elements to the cosmic microwave background radiation discovered in 1964, it also hinted at deeper forces at work. The most dramatic shift in recent cosmology came in 1998, when two independent teams of astronomers, led by Saul Perlmutter, the other by Brian Schmidt and Adam Riasuste, type Ia supernovae as standard candles to measure cosmic expansion. What they found was completely unexpected. The universe's expansion wasn't slowing down due to gravity, as everyone had assumed. It was speeding up. This observation defied conventional understanding and introduced a term that would haunt physics for decades: dark energy. To account for the acceleration, cosmologists revived Einstein's once dismissed cosmological constant, a term he had included in his equations to allow for a static universe. Now, it appeared this constant, or something like, it was real, and it was not holding the universe in balance, but tearing it apart. Dark energy, which makes up nearly 70% of the universe's total energy density, became the dominant component of the cosmos. Yet we still have no idea what it actually is. Is it a property of space itself? A dynamic field? A signal that gravity works differently at large scales? Its discovery was a turning point, not because it solved a problem, but because it created a new one so fundamental that it threatens to rewrite the entire narrative of physics and cosmology. As dark energy reshaped the framework of cosmic expansion, parallel advances in technology allowed us to peer deeper into space and time than ever before. The Hubble Space Telescope, launched in 1990, revolutionized observational astronomy. It captured stunning images of distant galaxies, gravitational lensing, and the iconic ultra-deep field revealing thousands of galaxies in what had appeared to be a blank patch of sky. Hubble provided critical data on the rate of expansion, the age of the universe, and the distribution of matter. But even more transformative was the launch of the James Webb Space Telescope, JWST, in 2021. With its infrared sensitivity and enormous primary mirror, JWST began revealing galaxies that formed just a few hundred million years after the Big Bang, probing an era never before observed. Its early findings challenged expectations. It detected massive galaxies that seemed too large, too well-formed, and too mature for their epoch. This raised questions about our understanding of galaxy formation and cosmic timelines. Could our models be wrong? Could dark matter behave differently in the early universe? Could the laws of physics themselves evolve? Other missions and instruments have contributed to this mounting shift. The Planck satellite refined measurements of the cosmic microwave background, allowing cosmologists to determine the composition and curvature of the universe with incredible precision. Meanwhile, experiments like LIGO and Virgo detected gravitational wave ripples in spacetime caused by merging black holes and neutron stars, proving Einstein right once again and opening a new window for observing the universe. These waves carry information about events otherwise invisible, and their detection marked the birth of gravitational wave astronomy, a field still in its infancy, but with the potential to reveal the unseen structure of the cosmos. Simultaneously, surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey mapped the large-scale structure of the universe, tracing the cosmic web of galaxies and voids shaped by dark matter and cosmic expansion. These maps are not just cartographic, they are forensic tools, helping scientists reconstruct the early universe and trace the fingerprints of dark energy across time. These observational tools have forced cosmologists to rethink core concepts. For instance, the discrepancy between measurements of the Hubble constant, known as the Hubble tension, may indicate the presence of unknown particles or forces in the early universe. This tension, combined with the unexpected galaxy formations observed by JWST, hints at a universe that is more complex than we thought, a universe that perhaps contains undiscovered physics beyond the standard model. Some theorists propose early dark energy, a form of repulsive energy that briefly influenced the universe before fading. Others suggest modifications to general relativity or the existence of sterile neutrinos. All of these ideas point toward a deeper structure beneath the equations we currently use as second turning point, still forming, in which the universe reveals not a single thread of truth, but a woven tapestry of interconnected mysteries. This moment in Historia Momentus, not unlike standing on a cliff, overlooking a vast sea that stretches beyond sight. Behind us lie the hard-won truths of physics, the triumphs of Newton, Einstein, Dirac, and Hawking, the verified models of nucleosynthesis, inflation, and structure formation. But ahead lies something stranger. The realization that dark energy dominates the universe and that it may cause an eternal acceleration means that galaxies will eventually vanish over the horizon, becoming forever unreachable. The observable universe will shrink, even as the actual universe grows. Future civilizations may find themselves in a sky without galaxies, unaware of the truth we now see. This cosmic loneliness, born not of emptiness, but of expansion, is perhaps the most poetic consequence of the turning point we've reached. We live at a privileged time when the light of distant galaxies still reaches us, when we can still hear the echoes of the Big Bang and trace the shape of the invisible scaffolding that binds the universe together. This is the turning point not just of knowledge, but of urgency. We now understand that the universe is accelerating toward a future of increasing isolation. We now suspect that our current theories, while powerful, are incomplete. We now possess the tools to look deeper, but what we find increasingly defies our expectations. And so we stand on the threshold of a new cosmology, one that will require not just new equations, but new ways of thinking. We must question what we take for granted, reimagine the nature of time, gravity, and space. We must prepare for answers that challenge the very notion of what reality is. Yet, the turning point is not an ending. It is an invitation, a signal that we are entering the next phase of human inquiry. It is the realization that the greatest discoveries often come not from solving a mystery, but from realizing the mystery is even bigger than we thought. Dark energy, early galaxy formation, the tension in Hubble's constant, the whispers of new particles, these are not failures. They are signs that the universe is still speaking to us, still revealing its secrets, one surprising clue at a time. Each new revelation is not a final word, but a key to a deeper question. Each boundary we push becomes the beginning of a new horizon. And so, in the age of space telescopes and quantum detectors, of AI-assisted research and interstellar probes, the turning point is not defined by a single discovery, but by the growing awareness that the universe is more complex, more beautiful, and more mysterious than we ever imagined. It is the recognition that the story of the cosmos is not finished. It is just beginning again. What if everything we know about the universe, its expansion, its structure, even its very dimensionality, is not wrong, but deeply incomplete, distorted by the limitations of our perspective? For over a century, physics has progressed by pushing outward, mapping galaxies, measuring cosmic radiation, calculating distances to the edges of space. But what if the next breakthrough requires us not to look farther, but to look differently, to shift the very framework of our inquiry and ask whether the universe is not what it seems, not a vast three-dimensional playground stretching infinitely in all directions, but something far stranger? Could it be that the universe, as we experience it, is not the full story, but a projection, an emergent phenomenon arising from more fundamental principles that do not resemble space, time, or matter as we understand them? This shift in perspective is more than a thought experiment. It is an active line of inquiry in modern theoretical physics, one that challenges not only how we study the universe, but what we believe it is. Among the most provocative of these reimagined perspectives is the holographic principally theory, born not in the study of light or optics, but in the paradoxes of black hole physics. In the 1970s, Stephen Hawking famously showed that black holes emit radiation due to quantum effects, eventually evaporating over time. But this led to a disturbing paradox. If black holes can evaporate, what happens to the information about the matter that fell into them? According to quantum mechanics, information cannot be destroyed, but according to general relativity, it must vanish inside the singularity. The tension between these principles pointed to a fundamental problem in our understanding of space, time, and entropy. In the 1990s, physicists like Leonard Susskind and Gerard 't Hooft proposed a radical solution. Maybe all the information in a volume of space can be described by data encoded on its boundary, much like a hologram stores a three-dimensional image on a two-dimensional surface. In this view, our three-dimensional universe could itself be a holographic projection, arising from a deeper two-dimensional structure existing on a cosmological horizon. The implications are staggering. If true, it means that our lived experience of space and time may be a kind of emergent illusion, a macroscopic result of microscopic informational laws that operate at the universe's edge. This perspective gained further traction through the development of the ADS-CFT correspondence by Juan Maldacena in 1997. A mathematical duality in string theory, showing that a gravitational theory in a five-dimensional bulk spacetime, anti-de Sitter space, can be exactly equivalent to a quantum field theory without gravity on its four-dimensional boundary. Though our universe is not ADS but de Sitter, due to positive cosmological constant and accelerated expansion, this duality proved a conceptual turning point. It demonstrated that gravity in space might emerge from lower-dimensional quantum mechanics, a realization that fundamentally alters our assumptions about what is real. The holographic principle is not merely metaphor, it could be the basis for a unified theory of quantum gravity. Reconciling general relativity with quantum mechanics, it suggests that the true nature of reality may be encoded not in the fabric of space, but on its edges, in patterns of quantum entanglement that create the illusion of continuity and depth. Such ideas lead us to reevaluate long-held notions of causality, locality, and dimensionality. For example, entanglement, the quantum phenomenon, in which particles become linked, such that the state of one instantly influences the state of another, no matter the distance, challenges the idea of separable, local events. If entanglement is not just a feature of particles, but the scaffolding from which space itself is built, then here and there are relative concepts. Work by physicists like Mark van Ramstonk suggests that the connectivity of spacetime may arise from patterns of entanglement, meaning that geometry itself is not fundamental, but a side effect of quantum information flow. This radically shifts the questions we ask. Instead of asking, "What is the universe made of?" we may begin to ask, what information patterns generate the appearance of matter, space, and time? The map changes, the ontology changes, even the concept of where something is becomes entangled with what it is and how it is known. This paradigm shift is not confined to theory. It reshapes scientific discussions in cosmology, astrophysics, and beyond. Take the cosmic expansion, for instance. Traditionally, we describe it as space itself stretching, carrying galaxies apart. But if space is emergent, then expansion might be the visible symptom of a deeper shift in the underlying information structure. Similarly, dark energy, rather than being a mysterious fluid-filling space, might be a manifestation of entropy dynamics at the cosmological horizon. In fact, Eric Verlinde has proposed that both gravity and dark matter effects could emerge from entropic principles, not from unseen particles, but from the statistical behavior of information. Though still speculative, such ideas redirect inquiry away from particles in space to principles beyond space, forcing physicists to reconsider the foundation upon which their models rest. Another shift in perspective comes from quantum cosmology, which suggests that the universe itself must be described as a quantum system. In this view, time may not be a fundamental backdrop, but a parameter that emerges from decoherence, the process by which quantum systems interact with their environment, giving rise to classical behavior. In the early universe, before such decoherence, time may have had no meaning. The question, what happened before the Big Bang, may be meaningless because before requires time to exist. This forces a new way of thinking about originaut as a temporal event, but as a transition from a timeless quantum state to the classical universe we observe. The Wheeler-DeWitt equation, a central equation in quantum gravity, famously lacks a time variable. It suggests a block universe in which all moments coexist, and what we experience as the flow of time is a perspectival illusion or consciousness moving through a static landscape of possibilities. The broader scientific community is increasingly receptive to such shifts, not because they are easy to grasp, but because they are necessary. The evidence demands it. The incompatibility of general relativity and quantum mechanics, the paradoxes of black holes, the strange behavior of the early universe all point to a deeper layer of reality that current paradigms cannot fully describe. Shifting perspectives is hard. It challenges careers, institutions, and epistemologies. But science evolves not by comfort, but by necessity. Every previous revolution in physics, Copernicus, Newton, Einstein, Bohr, required a radical reimagining of the cosmos. Today's emerging frameworks may be the next such leap. Moreover, the role of quantum mechanics in cosmic structure cannot be overstated. Though quantum effects are most noticeable at small scales, they shape the large-scale structure of the universe as well. The inflationary period that gave rise to the distribution of galaxies was driven by quantum fluctuations magnified to cosmic proportions. The seeds of stars, galaxies, and planets were sown not by classical mechanics, but by uncertainty, by probability, by the random jitter of a quantum field in a high-energy vacuum. This is perhaps the most poetic shift in perspective, the realization that the vast beauty of the night sky, the spirals of galaxies, the birth of stars, the whisper of cosmic radiationis, the amplified shadow of quantum chaos. The vast was born from the tiny. The stable was born from the uncertain. The universe is not built from billiard balls, and Clockwork Gearset is built from the fluctuations of fields, the logic of entanglement, and the language of Hilbert spaces. In parallel, alternative theories like causal set theory, emergent spacetime, non-commutative geometry, and even cellular automata-based models suggest that spacetime might not be continuous at all. Instead, it might be digital, discrete, or derived from abstract mathematical structures. These models challenge the classical assumption of smooth geometry, positing instead that space and time emerge from deeper causal relationships or logical operations. Some go further, suggesting that the universe operates like a quantum computer, processing information and generating structure according to probabilistic rules. These aren't science fiction. They are active areas of research, seeking testable predictions, striving for coherence with known data. They represent a willingness to re-examine everything, to say, perhaps we've been asking the wrong questions. This shift also transforms our sense of agency and meaning. If the universe is a hologram, an emergent computation, or a vast entangled network, then consciousness or awareness, our sense of self, must also be viewed in that context. Perhaps consciousness, like space-time, is not fundamental but emergent. Perhaps it arises from quantum coherence in biological systems, as some theories of quantum biology suggest. Or perhaps, like space, it reflects deeper informational processes that we do not yet understand. This isn't metaphysics, it's a scientific frontier. Because as we probe deeper into reality, the boundary between the observer and the observed begins to blur. Quantum mechanics tells us that the act of observation influences the system. But what happens when the observer is the system? When the consciousness asking the question is itself made of the same informational substrate it seeks to understand. The shift in perspective is no longer academic. For centuries, humanity sought to reduce the cosmos to a series of predictable laws, elegant, precise, absolute. From the celestial clockwork of Newtonian mechanics to the space-time curvature of Einstein's general relativity, each advancement promised a universe increasingly within reach of comprehension. But as our instruments sharpened, our simulations deepened, and our observations stretched across cosmic time, an unexpected twist emerged that undermines not only our models, but the very premise that the universe is orderly, self-contained, and singular. The more we search for a unifying theory, the more we are faced with the possibility that we live not in the universe, but in a universe one of countless others. And perhaps even more radically, that what we call the universe is not even real in the way we think it is. Whether through multiverse theory, the simulation hypothesis, or emergent cosmologies rooted in quantum information, we are now forced to confront ideas that defy the foundation of physical realism, suggesting that the deepest truths about existence may lie beyond observation, beyond falsifiability, and beyond anything our species has yet dared to imagine. This shift began subtly, with anomalies that defied explanation. The cosmological constant, the value representing dark energy, was inexplicably small but non-zero, a fine-tuning so extreme that it seemed improbable in a single universe context. The strength of gravity, the ratio of fundamental forces, the masses of elementary particles all appeared to be exquisitely set for the emergence of life and structure. Too much dark energy, and galaxies couldn't form. Too little, and the universe would recollapse. Too strong a nuclear force, and stars would burn too quickly. Too weak, and no atoms would exist at all. These anthropic coincidences led to the controversial resurrection of an old idea. Maybe the laws of physics are not universal, but local. Maybe there are countless other universes, each with different laws, different constants, different realities, and we just happen to exist in one where conditions allow observers like us to emerge. This is the essence of the multiverse theory, and while it began as a fringe speculation, it has become increasingly central to cutting-edge theoretical physics, especially in the context of string theory and inflationary cosmology. Inflation, the rapid exponential expansion thought to have occurred fractions of a second after the Big Bang, provides the mechanism. In many models of eternal inflation, quantum fluctuations cause different regions of the expanding space to undergo inflation at different rates, leading to bubble universes that form in isolation from one another. Each bubble may have its own laws of physics, shaped by the way extra dimensions compactified or how symmetry broke in that region. If true, this means our observable universe is just one patch of a much larger multiversia cosmic archipelago in an infinite sea. The multiverse is not a single theory, but a family of ideas, including the Level 1 multiverse, regions beyond our observable horizon. Level 2, different post-inflationary domains. Level 3, the many worlds interpretation of quantum mechanics. And Level 4, the realm of all mathematically possible structures. Critics argue these models are untestable and unfalsifiable, but defenders counter that they are the logical extension of existing physics, that they solve problems of fine-tuning and make probabilistic predictions, even if we cannot observe other universes directly. Yet, even as the multiverse stretches our notion of reality outward, another twist turns it inward. What if our universe is not just one of many, but not fundamental at all? What if it is simulated? The simulation hypothesis, most famously articulated by philosopher Nick Bostrom, suggests that if any civilization becomes technologically advanced enough to simulate entire universes, including conscious beings within them, then simulated realities would vastly outnumber base realities. Statistically, then, it is more likely we are inside one of these simulations than the original universe. This idea may seem like science fiction, but it emerges from the same computational thinking that underlies much of modern physics. Quantum mechanics, with its probabilities, discretized energy levels, and observer-dependent outcomes, already behaves more like a computation than a deterministic clockwork. The holographic principle, likewise, suggests that the three-dimensional world may be encoded on a two-dimensional surface structure remarkably similar to how computer graphics work. And at the most fundamental levels, some physicists propose that space-time itself is emergent from quantum entanglement or from underlying informational rule accessionally, that reality is a kind of quantum computer running a cosmic algorithm whose outputs we call existence. What would it mean if the universe were simulated? It would mean that space, time, and matter are not absolute, but variables defined by a higher-level architecture. It would mean that the apparent constants of nature could be part of the codebase, not eternal truths. And it would mean that consciousness, the observer effect in quantum mechanics, might play a far more central role than previously thought. The simulation hypothesis isn't just about whether we are real. It questions what real even means. If subjective experience can be generated by simulated neurons firing in digital space, then reality becomes inseparable from perception. In this view, our quest to understand the universe becomes recursive. We are beings within the system trying to decode the system, unaware of the broader framework in which it runs. This mirrors ancient philosophical insights from Plato's cave to Descartes' demon, but now recast in quantum and computational terms. Alternative cosmologies go even further. Some theories posit that the universe has no beginning or end, that time itself is an illusion created by the entropic ordering of events. Others suggest that consciousness is not an emergent property of matter, but a fundamental aspect of the cosmos, perhaps the source from which space and time emerge. The participatory universe, a concept once explored by physicist John Archibald Wheeler, envisions a cosmos in which observation does not just reveal reality, it creates it. This idea is echoed in modern quantum interpretations, such as cubism, which holds that the wave function is not a physical object, but a tool for an agent's personal expectations about future experiences. In such frameworks, the line between mind and matter blurs. The universe becomes less like a machine and more like a process of unfolding awareness. All of this leads to a deeper realization, one that cuts through the equations and data, the speculation and theory. Whether we live in a multiverse, a simulation, or an emergent hologram, the common thread is that our current picture of the universe is provisional. The unexpected twist is not that the universe is vast or complex. We already knew that. The twist is that it may be fundamentally beyond objectivity, that our role as observers is not peripheral, but central, that we are not just mapping the cosmos, but participating in it. We are part of the computation, part of the entanglement, part of the story. The universe is not out there. It is also in here. Every time we measure a particle, ask a question, or experience a moment of awe under the stars, we are not just studying the cosmos, are reflecting it. We are being it. This reframes the ancient question of our place in the cosmos. We are not cosmic accidents, nor are we cosmic royalty. We are emergent phenomena within a system whose scale and structure may be unknowable, but whose patterns we can glimpse through logic, mathematics, and experience. Whether that system is the base reality or one of many, whether it is simulated, conscious, or something else entirely, the fact remains. We are here, and we are capable of asking. That is the unexpected twist, that the universe produces beings capable of wondering what it is, of constructing models that push beyond their own sensory limits, of imagining realities beyond their own. The twist is not only in the theories, but in the capacity to make them. As we stand on the edge of this conceptual precipice, the questions multiply. Are there hidden variables determining our reality? Can we ever access information beyond our cosmic horizon? If the simulation ends, do we? If the multiverse is real, can we ever know what makes our universe distinct? These questions are not distractions. They are the next phase of inquiry. They point to a future where physics, philosophy, information theory, and cognitive science converge, where the boundaries between disciplines dissolve, as the boundaries of the universe once did. The unexpected twist is that we must now reimagine science. It's not just as a method of uncovering facts, but as a journey through possibilities, through frames of reference, through layers of understanding that reveal not certainty, but deeper kinds of mystery. In this mystery lies not despair, but wonder. The unexpected twist is not a dead end, it is a doorway. A signal that the narrative we thought we were writing has changed genre from science textbook to metaphysical epic, from geometry to poetry, from map to mirror. The next chapter of cosmology will not be about confirming old models. It will be about building new ones, braver, broader, more willing to confront the unknown. And in doing so, we will not just learn about the universe, we will learn what it means to ask at all. Despite the enormous strides humanity has made in understanding the cosmos, charting the age of the universe, tracing the formation of galaxies, detecting gravitational waves, and peering billions of years into the past, an overwhelming truth looms over the field of cosmology. We have only scratched the surface. The questions that remain are not trivial gaps to be filled with finer measurements or longer equations. They are profound structural challenges that cut to the heart of what reality is. The mysteries of dark energy and dark matter, the origins of cosmic inflation, the nature of time, the problem of unifying gravity with quantum mechanics, and the possibility of parallel universes or simulated realities, all pose challenges that current technology and methodologies are not equipped to fully address. As the universe expands, so too does the boundary of the unknown, and with it, the complexity of the tools we need to explore it. Future research must overcome not only technological and observational limitations, but also conceptual and philosophical ones, redefining what it means to know and what it means to observe. One of the most immediate and pressing challenges is the limitation of current observational technologies. Even the most advanced space telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope, are restricted by fundamental constraints: the speed of light, the transparency of the universe in different wavelengths, the noise from intervening matter, and the physical limitations of mirror size, detector sensitivity, and data transmission. Although JWST has opened new frontiers in infrared astronomy, allowing us to glimpse the first billion years after the Big Bang, we are still blind to what lies before the era of recombination. Roughly 380,000 years after the Big Bang, when the universe was opaque to electromagnetic radiation. This cosmic dark age holds vital clues to the formation of the first stars, black holes, and structures, but it remains largely inaccessible to optical and infrared observation. To probe this era, scientists are turning to alternative signals, especially 21-centimeter hydrogen line emissions, which can potentially provide a map of neutral hydrogen before the first galaxies formed. However, detecting such signals requires instruments that can isolate extremely faint radio emissions from a sea of galactic foreground noise, Earth-based interference, and ionospheric distortion. Projects like the Hydrogen Epoch of Reionization Array, HERA, and the Square Kilometer Array, SKA, aim to address this, but success will demand unprecedented precision, calibration, and data processing capabilities. Moreover, gravitational wave astronomy, though revolutionary in its detection of black hole and neutron star mergers, is still in its infancy. Future missions like LISA, Laser Interferometer Space Antenna, will aim to detect lower-frequency gravitational waves from supermassive black hole collisions and possibly signals from the early universe itself, an avenue that may one day allow us to see beyond the cosmic microwave background. Another major hurdle lies in the mystery of dark matter and dark energy, which together constitute about 95% of the universe's total energy mass content. Despite decades of indirect evidence, galactic rotation curves, gravitational lensing, and large-scale structure, dark matter remains invisible and unidentified. Countless experiments have sought to detect weakly interacting massive particles, WIMPs, axions, or other exotic candidates, yet none have yielded definitive results. The failure to detect dark matter in underground labs or at the Large Hadron Collider has forced physicists to broaden their hypotheses, considering alternatives such as sterile neutrinos, primordial black holes, or modifications to the laws of gravity, such as MOND or emergent gravity theories. The detection of dark matter, whether via particle physics, astrophysical observations, or gravitational anomalies, remains one of the greatest challenges in modern science. Dark energy presents an even more elusive problem. Its discovery in the late 1990s transformed cosmology, revealing that the universe's expansion is accelerating. But what drives this acceleration remains completely unknown. Is dark energy a constant property of space, as Einstein's cosmological constant would suggest? Or is it dynamic, evolving over time, perhaps the manifestation of a quantum field, or interaction with hidden dimensions? Answering this requires measurements of cosmic expansion across time with exquisite accuracy tracking, not just how fast galaxies move apart, but how the rate of that expansion has changed. Missions like Euclid, ESA, and the Nancy Grace Roman Space Telescope, NASA, are designed to map the geometry of the universe and the growth of cosmic structures with enough detail to constrain the nature of dark energy. But even these missions may only sharpen the mystery, not solve it. The possibility remains that dark energy is a placeholder for a deeper, undiscovered aspect of reality symptom, not a substance. To address these immense questions, scientists are calling for a new generation of space missions and instruments that exceed current capabilities by orders of magnitude. These include proposals for next-generation observatories, like LUVOIR, Large UV, Optical, IR Surveyor, which would offer vastly improved sensitivity and resolution over Hubble and JWST, enabling direct imaging of exoplanets and detailed studies of galaxy evolution. The Origins Space Telescope aims to probe the cold universe dust, gas, and molecular clouds where stars and planets are born. Meanwhile, ground-based projects like the Extremely Large Telescope, ELT, and the Vera-C Rubin Observatory will revolutionize time-domain astronomy, mapping transient events like supernovae, black hole mergers, and possibly signatures of unknown physics. These tools will generate petabytes of data, necessitating the development of AI-assisted analytics and quantum computing to detect subtle patterns and anomalies invisible to human analysis alone. Alongside hardware, scientists must also overcome theoretical and conceptual challenges. The search for a unified theory of physics zone that merges general relativity and quantum mechanics remains one of the great unsolved problems of science. String theory, loop quantum gravity, causal dynamical triangulations, and other approaches have yet to produce experimentally testable predictions. The hope is that quantum cosmology, holography, or the study of black hole thermodynamics may offer a breakthrough, but, as of now, no consensus exists. Even the concept of time, so fundamental to classical physics, is being re-evaluated. In quantum gravity, time may not be a fundamental parameter, but an emergent property of entanglement and decoherence. This raises profound implications for causality, cosmological origins, and the ultimate fate of the universe. To confront these unknowns, scientists are adopting new strategies. One is multi-messenger astronomy, the simultaneous observation of phenomena through different carriers of information light, gravitational waves, neutrinos, and cosmic rays. By combining these signals, astronomers can build a more complete picture of astrophysical events, testing theories from multiple angles. Another strategy is the increasing use of simulations and machine learning, where supercomputers model complex systems such as galaxy formation, dark matter behavior, and early universe inflation across vast scales and parameter. These simulations not only predict observational signatures, but also guide the design of future experiments, highlighting where anomalies or surprises might arise. In parallel, some scientists are advocating for a philosophical broadening of science itself, recognizing that certain questions may require new methodologies or frameworks. If multiverse theories are correct, and our observable universe is just one realization of many, then we may never be able to test these theories directly. Yet they may still offer explanatory power, consistency, and coherence within broader mathematical structures. Similarly, If quantum mechanics is incomplete or requires reinterpretation via hidden variables, objective collapse models, or observer-based formulations, then we must be prepared to challenge long-standing assumptions about what science is supposed to be. The border between physics and metaphysics, once sharply guarded, may blur in the coming decades as we probe questions that hover at the limits of testability. Despite these formidable challenges, the spirit of exploration remains undiminished. There is an extraordinary global collaboration underway among space agencies, universities, private companies, and citizen scientists to tackle the unknown. Public interest in space, sparked by high-profile missions and commercial ventures, has brought renewed energy and investment to the field. The democratization of science through open data and collaborative platforms has allowed students and amateurs to contribute to discovery. And as artificial intelligence grows more sophisticated, it will increasingly become a partner in the scientific process, not replacing human insight, but amplifying it, accelerating pattern recognition, hypothesis generation, and real-time anomaly detection. In the end, the biggest challenge may be cognitive: how to remain open in the face of the unfamiliar, how to ask questions we don't yet have language for, how to interpret findings that upend everything we thought we knew. Scientific progress is often nonlinear. It advances not just through accumulation of data, but through paradigm shifts where old assumptions give way to new frameworks. We may be approaching such a moment now. Just as Newtonian physics yielded to relativity and quantum theory, so too may our current models give way to a more complete cosmology, one that incorporates information, consciousness, entanglement, and complexity in ways we are only beginning to glimpse. The universe is not just a puzzle waiting to be solved. It is a horizon that keeps receding, a mirror that reflects our questions back to us, each answer revealing a deeper layer of ignorance and wonder. The challenges we face are not walls, they are invitations. They are the next set of clues in a cosmic riddle that has been unfolding since the first moment of time. And while we may never find all the answers, the search itself will continue to redefine what it means to be human, it just as observers of the universe, but as participants in its story. As cosmology enters its most ambitious and bewildering era, it is fast approaching a kind of final confrontation, a collision not of personalities or institutions, but of ideas that threaten to reshape the very foundation of how we understand existence. For more than a century, physics has operated under two distinct but immensely successful paradigms: general relativity, which describes gravity and the behavior of space and time on cosmic scales, and quantum mechanics, which governs the strange, probabilistic world of the very small. Each theory is precise, predictive, and experimentally verified within its own domain. Yet when brought together, such as at the edge of a black hole or the first instant after the Big Bang, these models fall apart. Their equations contradict one another. Their assumptions clash. One is deterministic and geometric. The other is probabilistic and abstract. This incompatibility is not a minor problem, it is a chasm at the heart of modern physics. And yet, the universe must obey one consistent set of rules. This unresolved tension has fueled the rise of the latest generation of competing theories, each aiming not just to explain the universe, but to unify its laws into a single, coherent framework. Among these contenders, string theory remains one of the most prominent. At its core, string theory proposes that the fundamental building blocks of reality are not particles, but vibrating one-dimensional strings. These strings can exist in multiple modes of vibration, each corresponding to a different particle, including the graviton, the hypothetical quantum of gravity. String theory elegantly unites gravity with quantum mechanics, and naturally requires extra spatial dimensions, typically 10 or 11 in total. Its mathematical consistency and ability to incorporate all known particles make it a leading candidate for a theory of everything. However, string theory's great strength is also its greatest weakness. It is so flexible that it allows for an enormous number of possible universes, estimated at 10 circumflex 500 or more in the so-called landscape of solutions. Critics argue that this makes it untestable and unfalsifiable, but supporters counter that the multiverse, as predicted by eternal inflation and string theory, could explain the fine-tuned constants of our universe not as cosmic accidents, but as environmental features selected by anthropic reasoning. Another major effort to reconcile relativity and quantum mechanics is loop quantum gravity, LQG, Unlike string theory, which posits that space-time is smooth and continuous, LQG proposes that space itself is made up of discrete loops, woven into a network like the pixels of a digital image. This quantization of space could eliminate the singularities predicted by general relativity, such as those inside black holes or at the beginning of the universe. In LQG, the Big Bang is replaced with a Big Bounce, where a previous contracting universe led to the current expansion. LQG has had success in constructing a background-independent quantum theory of gravity, but it struggles to incorporate matter and forces in the same way string theory does. The strength of LQG lies in its minimal assumptions and its grounding in canonical quantization. The debate between string theorists and loop quantum gravity advocates continues to shape the landscape of theoretical physics, each offering insights, but neither yet providing conclusive experimental evidence. Adding complexity to the final confrontation is the growing interest in emergent gravity and entropic gravity models, such as those proposed by Eric Verlin. These suggest that gravity is not a fundamental force at all, but an emergent phenomenon arising from changes in the information content of space-time. In this view, space, time, and even gravity itself are macroscopic phenomena analogous to temperature or pressure emerging from the statistical behavior of microscopic degrees of freedom. This approach reframes gravity not as a force to be quantized, but as a side effect of information theory. Such theories are appealing because they provide potential explanations for dark matter and dark energy without requiring exotic particles. Yet they are still in early development and have yet to make precise predictions that can be tested observationally. Still, their presence in the theoretical ecosystem illustrates a growing willingness to rethink not just how the universe works, but what it fundamentally is. All these theories, with their elegant equations and imaginative frameworks, orbit the same gravitational center, the unresolved question of the universe's boundary. Will we ever find it? Is there a true edge to the universe, a wall, a frontier, a final layer? Or is the notion of a boundary itself a misinterpretation, a product of our classical intuitions imposed on a quantum cosmos? In general relativity, the universe can be finite yet unbounded, curved, like the surface of a sphere in four-dimensional spacetime. But in quantum cosmology, even that smooth continuity may not exist. Space and time might be emergent, and the universe could be a projection from lower dimensional information, as the holographic principle suggests. In this case, the edge of the universe may be mathematical, not physical, a limit in how information is stored and organized, not a place one could travel to. Philosophically, the boundary question strikes at the core of human curiosity. We are creatures who evolved in bounded environments, forests, valleys, planet sand. We instinctively seek edges, endings, limits. Yet the cosmos resists such simplicity. The observable universe is bounded only by the speed of light and the age of the universe, about 46.5 billion light-years in radius. But this is not the whole universe. Beyond our horizon may lie infinite stretches of space we can never access. And if the universe is accelerating due to dark energy, then those regions are receding from us faster than light. We will never reach them, never communicate with them. In a profound sense, the future is shrinking. The universe is not infinite in what we can observe, even if it is infinite in extent. That conceptual wall between what exists and what can be known may be the true edge, and it is epistemological, not physical. This ongoing debate over the nature of the boundary intersects with the quest for a unified physics. If relativity and quantum mechanics can be reconciled, then the singularities of black holes and the Big Bang might be smoothed away, replaced with deeper structures that reveal what lies beyond. The unification would also provide the mathematical tools to describe the early universe more precisely, potentially answering questions about inflation, the origin of matter, and the asymmetry between matter and antimatter. Some physicists believe that quantum gravity will show that space-time itself is not fundamental, and that the universe is better described as a quantum computational process or a network of causal relationships. These radical ideas require new mathematics and new experimental pathways. Could future accelerators probe the Planck scale? Could quantum simulations mimic quantum gravitational systems? Could we use entangled photons to probe the fabric of space? These are not idle speculations. They are emerging research programs that may define the coming century of physics. The future of cosmology, therefore, is not just about deeper space, but deeper thinking. It will depend on next-generation telescopes like the Nancy Grace Roman Space Telescope, the Extremely Large Telescope, and proposed missions like LUVOIR and HabEx, which aim to directly image Earth-like exoplanets and map the expansion of the universe across billions of years. It will depend on quantum computing, which may allow us to simulate universes and explore theories that are currently beyond our computational reach. It will depend on AI systems that can sort through petabytes of data, finding correlations and anomalies invisible to the human eye. But most of all, it will depend on creativity and courage, in the willingness of scientists to follow the math where it leads, even when it leads beyond intuition, beyond familiarity, and perhaps beyond what we can measure. This final confrontation between competing theories, between observable boundaries and theoretical infinities, between the known and the unknowable, is not a crisis. It is the culmination of a long journey, the natural friction at the edge of knowledge, where real progress is made. In the end, we may not find a single, elegant answer that wraps the universe into a neat equation. We may find layers of truth, levels of approximation, frameworks that coexist rather than compete. We may discover that asking, "What is the true theory?" is like asking, "What is the one true language?" The answer depending on what we want to describe and from what perspective. Cosmology is no longer about drawing maps of stars. It is about drawing maps of reality itself. And as we confront the most abstract, most profound, and most unsettling ideas our species has ever produced, we do so not from a place of despair, but of expanding wonder. Because every theory, every contradiction, every unanswered question is a sign of vitality. The universe is not hiding, it is inviting. The final confrontation is not a battle to be won. It is a dialogue to be deepened, at a call to reimagine what it means to be conscious, curious, and cosmically alive in a universe whose ultimate truth may forever lie just beyond the next horizon. In the grand pursuit of understanding the cosmos, humanity has uncovered truths more profound than any ancient myth, more mysterious than any philosophical speculation, and more beautiful than any imagined story. We have peered into the heart of galaxies, measured the radiation left behind from the birth of time, and mapped the slow waltz of dark matter weaving its invisible web through the universe. And yet, for every answer we've found, 1,000 new questions have risen. This is not a failure, it is a testament to the infinite depth of the unknown. Beyond the mathematics, beyond the measurements, beyond the laboratories and observatories, there lies something deeply human at the heart of cosmic exploration. A moral story, a reflection of who we are and who we might yet become. The deeper meaning of exploring the unknown is not merely to satisfy curiosity, but to recognize our place in something far larger than ourselves, to grow in humility, unity, and wisdom, and to realize that our thirst for knowledge is, at its core, a quest for meaning. Curiosity is not a luxury of comfort, it is a fundamental trait of human survival and development. It is what pushed our ancestors to cross mountains, rivers, and oceans long before maps existed. It is what built cities, sparked revolutions, launched spacecraft, and decoded genomes. Curiosity is not just a desire to know, it is a refusal to accept ignorance as permanent. It is the engine of every field of progress. In science, curiosity is refined into a disciplined practice, willingness to confront uncertainty, to test assumptions, to admit error, and to expand understanding even when the path ahead is unclear. But when applied to the cosmos, curiosity becomes something even more powerful. A force that stretches the mind beyond its familiar boundaries. It teaches us to think in billions of years, in hundreds of billions of galaxies, in probabilities and paradoxes. It forces us to evolve intellectually and emotionally. It teaches us to ask questions, not just about the external universe, but about ourselves, our origins, our purpose, our future. Yet curiosity, for all its power, must be tempered by humility, because the universe is not obligated to be simple or intuitive or even fully knowable. There is a danger in assuming that all questions have answers, or that all mysteries will eventually yield to technology and intellect. Some aspects of reality may lie forever beyond our reach, not because we lack intelligence, but because we are embedded within the very system we are trying to observe. Our brains are wired for survival, not for quantum gravity. Our senses evolved to navigate landscapes, not space-time. Every step forward in cosmology is not only a triumph of ingenuity, but a confrontation with limitation. And in that confrontation, we find something deeply moral: the need to remain grounded, to remain aware that knowledge is never the same as wisdom. Just because we can explore the stars doesn't mean we always understand the meaning of what we find. The balance between knowledge and mystery is not a line to be crossed, it is a space to be lived in. The greatest scientific minds, from Newton and Einstein to Hawking and Sagandad, not claim to know everything. They spoke of wonder, of humility, of the music of the spheres, of the mind of God, not as final answers, but as expressions of awe. They understood that mystery is not the enemy of science. It is its guide. Mystery tells us where to look. It shows us where our theories break, where our instruments fail, where our imaginations must expand. In the face of mystery, science becomes more than a tool. It becomes a philosophy, a worldview, a way of living with open eyes and an open heart. It invites us not just to explain, but to experience, to stand beneath the stars and feel the smallness of the self and the vastness of possibility. Cosmic exploration teaches us not only about space and time, but about ourselves. It reminds us that we are united by a shared original humans, all life, all matter, all energy. We are stardust, born from the same ancient explosions that shaped galaxies and planets. The atoms in our bodies were forged in stars. The calcium in our bones, the iron in our blood, the oxygen in our lungs, they were not made on Earth, but in supernovae. This fact is not poetic metaphor, it is physics. And from this truth comes a moral imperative: to see each other not as strangers, but as relatives in the deepest sense. Cosmic knowledge dissolves artificial boundaries. It makes nationalism, racism, and sectarianism look absurd against the backdrop of 13.8 billion years of shared history. It reveals Earth not as a battleground, but as a fragile oasis suspended in an endless void. A single blue dot, as Carl Sagan so poignantly said, the only home we've ever known. In this view, cosmic exploration becomes a mirror. It shows us our arrogance and our wisdom, our cruelty and our compassion, our capacity for destruction and our potential for creation. When we look outward, we are also looking inward. We are forced to ask, what kind of species are we? What kind of species do we want to become? If we can send robots to Mars, if we can measure the echo of the Big Bang, if we can map galaxies billions of light years away, then surely we can feed the hungry, cure the sick, educate the forgotten, and care for the Earth. The challenge of the cosmos is not just to explore it is to become worthy of it, to match the grandeur of the universe with the greatness of our own behavior, to take the cosmic perspective and apply it not just to science, but to justice, empathy, and the way we treat one another. There is also a profound lesson in the fragility of life. The more we study the cosmos, the more we realize how rare and precious habitable conditions truly are. Planets with liquid water, stable climates, protective magnetic fields, and complex ecosystems are not inevitable. They are miracles of balance. And despite the possibility of life elsewhere, Earth remains the only place we know where consciousness arose. This raises an enormous ethical question. If we are alone, even temporarily, then the responsibility to preserve and protect life becomes not just environmental or political, it becomes cosmic. Our actions matter. Our choices ripple outward. In the vast silence of space, Earth is not just a planet. It is a beacon of awareness, a carrier of story, a spark in the dark. This gives us another kind of moral takeaway: the need for long-term thinking. Cosmic timescales stretch into billions of years, but human history is measured in centuries and generations. This mismatch has caused much of our current crisis: climate change, resource depletion, geopolitical instability, all driven by short-term interests. Cosmic exploration encourages us to think differently, to see ourselves as part of an ongoing process, not a terminal phase, to invest in futures we will not live to see, to build not just for the now, but for the next 1,000 years. This is not utopian. It is necessary. The universe will continue without us. The question is, will we continue with it? And if we doif, we survive, evolve, and endurathen, the universe becomes a canvas for human creativity, courage, and cooperation. Colonies on Mars, probes to the Oort cloud, interstellar missions. These are not fantasies. They are possible futures, but they are also tests, not of technology, but of character. Can we avoid repeating the mistakes of Earth on other worlds? Can we build societies rooted in equality, sustainability, and wisdom? Can we explore without exploiting? Can we expand without erasing what makes us human? The stars do not care what we do, but maybe that's what gives us freedom. There is no script, no predestined outcome. We are the storytellers, the observers, the question askers. And in this, we find meaning not because the universe was made for us, but because we are capable of finding meaning in a universe that wasn't. That is the final moral takeaway. We are small, yes, but we are not insignificant. Our questions matter. Our actions matter. Our wonder matters. The cosmos may not provide all the answers, but it gives us something even greater. The chance to ask, the chance to grow, the chance to become more than what we were. In the end, exploring the unknown is not about conquering it. It is about being changed by it, about becoming more curious, more humble, more united, and more aware. It is about realizing that the greatest discoveries lie not only in distant galaxies, but in the ways we learn to treat each other, the Earth, and the future we all share. The universe is waiting, not to be claimed, but to be understood. And through that understanding, we may finally come to understand ourselves. As we stand at the edge of all we know, gazing into the silent, star-flecked abyss of the cosmos, it becomes tempting to ask for closure. We want a final theory, a single elegant equation, a neat ribbon tied around the infinite. We crave answers that give us control, clarity, and certainty. And yet, the more we explore the universe, the more it resists conclusion. Every discovery opens up a dozen new questions. Every solution reshapes the problem. From the smallest particles to the largest structures, from the origin of time to the fate of the cosmos, we find ourselves chasing shadows across an ever-shifting landscape of possibilities. And so, in the end, we must ask, should the mystery remain open, ended? Should we accept that the story of space, time, matter, and mind may not lead to a single ending, but to an endless series of revelations, each one deepening rather than resolving the mystery? There is deep value in leaving questions unanswered, not as a failure, but as an invitation. Mystery is not ignorance. Mystery is potential. It is what drives us to build telescopes and particle colliders, to launch missions to Mars, to write simulations of the early universe, to invent new mathematics and new languages of thought. Unanswered questions are not dead ends. They are portals. They keep science honest, imaginative, and alive. The moment we decide that we know everything is the moment we stop asking, stop growing, and stop becoming. But when we admit that we don't know, that we cannot know everything, we remain humble in the face of the infinite, and we give ourselves permission to evolve. Just as no one theory can contain the universe, no single conclusion should contain the human spirit. The biggest takeaways from our journey into the cosmos are not technical details or trivia. They are philosophical, moral, and existential realizations that come from seeing ourselves in context. First, we've learned that the universe is unimaginably vast, both in space and in time. It is not centered around us. It does not respond to our beliefs. And yet, within it, life and consciousnesses emerged. This simple fact reshapes everything. We are not special in scale, but we are special in capacity. We can ask, imagine, explore, and understand. Second, we've learned that the universe is governed by laws, deep symmetries, patterns, and structures that suggest a profound order underlying apparent chaos. But these laws may themselves be emergent, the product of deeper information processes, quantum geometries, or even multidimensional frameworks. What appears to be fundamental may not be what we call reality, may be a layered phenomenon. built from principles we have only just begun to glimpse. Third, we've discovered that space is not empty, it is alive with forces, particles, and fields. Dark matter, dark energy, gravitational waves, neutrinos, quantum foam. The universe teems with invisible phenomena, most of which we don't fully understand. This tells us that reality is not limited to what we can see. Our senses, our tools, even our current theories provide only partial access to the whole. And fourth, perhaps most importantly, we've realized that our greatest asset in navigating this mystery is not certainty, but curiosity. It is the willingness to live in the question, to refine it, to wrestle with it, and to grow with it. The universe does not yield its secrets easily, but it rewards patience, creativity, and the courage to rethink everything. In the centuries to come, we may develop technologies that make today's instruments look primitive. We may discover new dimensions, detect evidence of parallel universes, simulate the birth of the cosmos, or prove that space-time is emergent from quantum information. We may rewrite physics from the ground up, or we may find limits, boundaries to what can be observed, measured, or even conceptualized. And that, too, will be part of the story. Because the goal of science is not to eliminate mystery, but to deepen our engagement with it. To make the unknown not less strange, but more beautiful. The universe is not a problem to be solved. It is a conversation to be continued. Leaving the cosmic story open-ended does not mean abandoning hope or rigor. It means embracing a new kind of knowledge, one that includes uncertainty, paradox, and awe. It means recognizing that the journey itself is the point. We do not explore space to find a final answer. We explore because something in us yearns to understand, to connect, and to become. That yearning is what defines us as a species. It's what lifted us out of caves, pushed us across oceans, launched us to the moon, and sent our thoughts beyond the stars. It's what binds together every physicist and philosopher, every child who looks at the sky and asks, "What's out there?" Perhaps the universe will one day be understood not as a machine, but as a song of vast unfolding harmony of energies and probabilities, with no final note, only changing keys. Perhaps we'll learn that reality is not a place, but a process. That consciousness is not an accident, but an aspect of the whole. That the cosmos is not just what surrounds us, but what we are. And even if we never find the ultimate theory, the search will continue to change us. It will teach us patience. It will demand humility. It will forge connections across cultures, across centuries, and across disciplines. In the process of reaching outward, we will reach inward and discover that the most important frontiers are the ones we carry inside. So no, the mystery should not be closed. The final answer should not be forced. The horizon should not be brought to an artificial end. The unanswered question should remain like the stars themselves, as a reminder that we are still becoming, still reaching, still learning how to see. Because in a universe as vast and mysterious as ours, the absence of closure is not a lack, it is a gift. It is a call to wonder, a call to listen, a call to go on. In this open-ended ending lies the truest reflection of the universe itself, a story that has no final chapter, only unfolding pages waiting for us to turn them.